so. So instead of me recording the video that's on the screen, this is recording video in my voice on a disc, and in the end I'll upload that to our class for those who need to take a look at it and catch that. So at the very end of our day last day, I talked about the way light travels. And does anybody remember the two requirements for how light traveled? How does light travel? What are our requirements for the way in which light travels? Sorry? No, not energy and length. You're thinking too complicated. Yep. Straight. It travels straight. And I drew an example of how we know that light travels straight. What was I trying to draw at the end to represent what happens when light travels straight? What do we see? What effect do we see that proves to us that light travels nice and straight? Yep. We see shadows. We see distinct shadows. We looked at what happens when the light source is small. I can actually use this light source as a small light source and a large light source. If I put my hand far away, because that lamp is so far away, to my hand way out here, that light source appears to be small. And you can see there I've got a nice, sharp, defined shadow. I've got an umbra that's very dark. But if the source of light is large, and I can use this as a large light source by putting my hand close to it, all right, if I put my face right there, I would be blinded because of such large light source. And you'll notice that my shadow looks fuzzy. And that's because light is able to sneak around my hands because of the large light source. And when we have a large light source, we have a dark part of the shadow, the umbra, but then we have this kind of gray part of the shadow, and that was called the penumbra. All right, and that's exactly where we finished the last day. So today we want to talk about what happens when light encounters objects. And so our title, and I'm going to do this right here, is Reflection of Light. All right, so my title is Reflection of Light. Now, before we talk about reflection in itself, first, let's talk about when light strikes an object. So, what can happen when light strikes an object? All right. Well, we already talked about this a little bit. There are three things that can happen when light hits an object. What are those things? You take the earbud out of your ear, please, there. Yep, awesome. What can happen? Cade, what can happen?
It can reflect.
It can be reflected. Excellent, I'll write that down. It can be reflected, and we'll draw that up in a minute. Number two, what can happen? Yep. It can pass through it. That's called transmitted, and I'm going to put that down as number three. It can be transmitted. And the reason I'm putting that at the end is because I just want to add some sub things to the transmitted part. What else? Yep. It can be absorbed. Absorbed. All right. When things are reflected, they can appear to be shiny. Shiny. I'm terrible with spelling shiny. I always put shinny. Is it like one N? Shiny? Two N's? Shiny? I don't know. They can be shiny. Things can be shiny if it's reflected a lot, okay? Absorbed, things can be dull, right? Things can be dull. In other words, there's not a lot of light coming off of it, okay? Now for transmitted, there's actually three possibilities that we can have there. So underneath transmitted, I'm going to put A, and I'm going to move things up a little bit. We already know different ways to describe the transmission of light. We've been using them to describe our substances that we've been talking about when dealing with chemistry. And those are those words that we use to talk about how the light can be associated with it. So one we know as transparent, translucent, and then the last one is opaque. What does it mean to be transparent again? If it's transparent, what happens? What's that? You can see right through. So in other words, the light is able to go through easily. The light is able to pass through easily. Easily. All right? The light is able to pass through easily. When we look at it, we can see a clear image of what we're looking at. A clear image can be seen. All right? Our rulers are transparent. So I can easily see what that writing is as we look through the rulers. The second one, B, translucent. We know that as well. Translucent. All right? So translucent. It means that you can't see a clear image. Only some of the light can get through. Some of the light, and I'm just taking a look to make sure I'm not writing off to the side. Some of the light goes through and some is absorbed. Some goes through and some is absorbed. And in this case, you cannot see a clear image. All right, so you cannot see a clear image. An example of something that's translucent is simply just a piece of paper. All right, so if I take a piece of paper here and I just hold it up here like so, and I put my hand behind it and it's got a little bit of light in there, I can see my hand there, right? But I can't see the actual distinct features of my hand. I can just kind of see that there's something there, so I can kind of see through it. Excellent, translucent. And the last one there, C, is opaque. Opaque. All right, and no light can go through. All right, no light can go through, and therefore no image can be seen. Can be seen. All right? And no image can be seen. So no light can go through and no image can be seen. If I were to draw a little sketch of those, so I'm going to just draw like some panes or maybe pieces of wood and various things. So I'm going to put a dividing line in there. I'll draw a second one there and put a dividing line in there. So if I've got some rays of light coming, all right, and if this is transparent, what do those rays do? If it's transparent, what are those rays going to do? They're going to pass straight on through. No effect. So the rays are going to go right on through. All right? The rays went right on through there. Let's make that a little clearer if we can. There we go. If this one here is translucent, and I got some rays coming in, what's going to happen to some of those rays? And what's going to happen? Yeah, what's going to happen? What are the possibilities if it's translucent? Some will go through. We'll have one go through like this. I'm going to have one go through and kind of go off on an angle because sometimes it can be deflected. That's why we can't see a nice clear image. And then I'm going to have one come back like that. All right? It doesn't really matter. They just don't all go through nicely. And on my last one, I'll put another block in here like this. And this is going to be opaque. I'm going to have 3 rays coming in. How many are going to get through? None of them will get through. Some might bounce back. We might see a reflection, but none will go through. Okay? So none of them will go through. So that's what happens when lights can encounter objects. So what do we want to look at for the next few days? For the next few days, we're going to be looking back here at reflected light. Once we've talked about all the different ways that light can be reflected from various types of mirrors, we will look at transmission, what happens when light goes through things like windows and lenses. And then at the very end, we'll talk about color theory, and that's what happens when things are absorbed. Yep?
You said when it goes to like windows and lenses, like would that be like when sun goes through my glasses?
Correct, exactly. When we talk about transmission, we will go through, we will talk about glasses and how they work and those types of effects. Correct. Okay, so that is kind of the beginning there. What we want to talk about right now is something called the law of reflection. The law of reflection. The law of reflection. All right. So we're going to be, and actually I'm going to grab a piece of equipment that we're going to be using when we do our lab. So we're going to be doing some labs here today, or one lab today, where we're going to study how light reflects from a mirror. All right, so there's a plastic mirror. It's fairly thin. You can see it's got a magnet on the back. Actually, I should grab the other piece of equipment that we're going to use. So you can see there, it's got a little magnet on the back. And the reason we put the magnets on the back of them is so that we can use a stand that looks like this, right? Looks like this. And I can stand that up, and then I can put my mirror on there, and then I can do some things. Now we need some light to shine at it. Now, the devices that we're going to use to shine the light at is something called a ray box. So a ray box is designed to have different light sources in here to be able to produce straight beams of light. All right, could you leave the phone alone, guys, for a bit? All right. So, straight beams of light. So the way this ray box works, it has a power supply. I've got it plugged into my power bar here, and I plug it in just right here at the back end. And it's got some LEDs in there, and I don't know if you can see that light in there. I think I blinded you there, right? I got you, right? A few of you guys, I can blind you guys out there. Excellent. And if I put that down on the piece of paper, you can see there it makes a nice little beam of light. And actually, if I bring my mirror in, you can see we can make that beam of light reflect, all right? Now, we're actually able to look into the mirror a little bit there because I'm not lined right underneath the camera there. Now I'm lined right underneath the camera. So we're going to be doing an experiment where we're going to be taking some light and we're going to reflect it off of some mirrors, and we're going to study how that reflected ray comes off of the mirror. That's what we want to study today. How does the reflected ray bounce off compared to the ray that's coming in? Again, you'll notice you can see into the mirror, but if I bring it right below the camera, there you can see now I'm right below the camera because you can't see into the mirror. So don't worry about this little part right here. Don't worry about that in there. That's inside the mirror. We're looking at what happens when it bounces off the mirror. And actually, if I line this up quite nicely, you can probably tell me what the law of reflection is. What happens to the ray? How do you think the ray bounces off compared to when it comes in if I change the angle? How would you describe the way it bounces off compared to the way it comes in? If we're just looking at this without doing any measurements and just looking at it, how would you describe the way that that ray comes off of the mirror, this guy here, compared to the way in which it comes in? What do you think, Nolan?
Like the angle it comes in, that's the angle it's going to go out.
So the angle that it comes in is that the angle's going to go out, yeah? That there's a symmetry to it. Exactly, that it's symmetrical. We know what symmetrical is, that we can kind of flip it over, it's the same thing. So exactly, so right there you've got a hypothesis. The hypothesis is that the angle it goes in is going to be the same as the angle it's going to go out. So in a moment, we're going to be doing an experiment where you're going to be doing 5 or 6 rays at different angles, and we're going to see whether those angles are true or not. Now what I need to do in order to help us explain what's happening, I need to draw a mirror so I can define some important things that we're going to be dealing with. So right now I'm going to get the ray box out of the way, we'll get to it, we'll get the mirror out of the way. This is the other mirror we're going to use. Notice that it's a big thick piece of glass, so it's a little different. It's a little more reflective than this guy because it's plastic versus glass. But because it's thick glass, we do run into a situation where the light actually has to go through the glass, and that's a little bit of a thing because the reflective part is actually at the back of the glass right there where my fingernail's pointing as opposed to at the front. But that's the other apparatus. So at this point we're going to draw a mirror, and this is the way we're going to always draw mirrors. So you can get your ruler out, and down near the bottom, kind of like where I had the mirror, on a line preferably, you can draw a line. Right there, draw the line. Notice I didn't get it exactly on the line. It does not matter at this point. So just draw a line to represent the mirror. Now, I'm going to put some marks here on the back side like this. All right. All right, and that represents the back of the mirror. All right, so these lines here represent the back of the mirror. And so the flat line is the front of the mirror. That's the shiny part. And I'm not going to try to spell shiny again. I already tried that once and it failed miserably. But the front part is the shiny part. So now what I'd like you to do is I'd like you to take your protractor. Because now becomes a very important thing. Actually, wait a minute. Do we want to do the protractor first? No, we'll do it second. Take your ruler and have a ray strike the mirror. It doesn't matter what angle. I like to put it off here to this right-hand side. So I'm going to just draw a line that goes in like this, and it hits the mirror. Okay? You want to draw a ray on your mirror. And we're going to put an arrow on it. Always put arrows on your rays because it tells us where the light is going. Now, we're going to have to figure out where to put this particular thing. So what we have to do is we have to draw a special line. All right? Actually, let's label a few things first. This is called the incident ray. The incident ray. Incident means incoming. The ray that's coming in. Okay? This spot right here where the ray hit is called the point of incidence. It's the point at which the ray hit the mirror. Now, we want to draw a proper reflected ray. We've been told it's symmetrical, and it is. And we've told that, or we believe that it's going to bounce out at the same angle it bounced in. Now you might think I could take my protractor and I could measure that angle right there. But we don't typically measure that angle when we do physics. When we start looking at things that are transparent, like water and glass and plastic, we don't like to use the surface to measure from. We like to use a line that is 90 degrees from the surface. So here's what we're going to do. Everybody following along. Protractor. Get your protractor. And put the point of incidence at the base of the point of incidence of the protractor. See it right there? See that spot right there? I've got that right where the ray hits. I'm going to go straight up. Notice how I've got the bottom line on the mirror, and I've got the point at the point of incidence. Everybody have that? I'm now going to go straight up, and I'm going to put a little mark up here above the 90 degrees. So I've put a mark right there above the 90 degrees. So I've got it on the mirror. I've got the mark on the point of incidence. I go straight up to 90 degrees and I mark it. Now I'm going to remove the protractor. I could use the protractor as a straight edge because I just need a line that's straight. And I'm going to connect the point of incidence to that mark that's 90 degrees. Right there. And I've created a 90-degree line. In physics, we call the 90-degree line a normal. I have no idea why mathematicians Have you got a protractor? Have you got a ruler? Have you drawn this picture? I don't believe you. Please participate and keep rolling. I don't know why it's called a normal. I have no idea. We use it in physics too. When something's sitting on a surface, we say that there's a normal force. It means 90 degrees or perpendicular. It doesn't matter. This angle in here between the normal and this ray, we call angle I. You've seen that little angle symbol before, I believe, correct? Have you seen that before? No? Little angle symbol in math? I'm going to write down here what that means. Angle I. Angle I is the angle of incidence. Right? It's the angle that it is incident. So we've got all the incoming information. We've got the incident ray. It strikes at the point of incidence. We've drawn our normal. We now have the angle of incidence. I'm now actually going to measure my angle of incidence. Yours will be different than mine. It depends on how you drew that. So here's how we measure it. I'm not going to use the protractor like this, because notice the zero lines are on either end of the protractor. So I'm going to turn it so that the zero is now on the normal, all right? And the 90 is on the mirror. So the zero is now up here on the normal, and the 90 is on the mirror. And now I'm going to measure 0, 10, 20, 30, 40. There's the 40 mark right there. 1, 2. My angle of incidence is 42 degrees. What is yours?
Same.
Did you get 42? That's awesome. That is awesome. You know what? When I normally do it, I often hit 45 because I put it kind of in the middle, right? So I'm going to write on here, angle I equals 42 degrees. I just wrote 44. Why would I write 44 when I said 42? Angle of incidence is 42 degrees, and I need an eraser. Angle of incidence is 42 degrees. What angles did you get? Logan, what did you get for an angle? 40? Nice. Anyone else want to share? I don't know why I'm doing this. I'm testing to see if somebody's actually done it or not. What do you got? 35. Josh, what'd you get? 40. Nice. So here's what we're going to do. We now know what the angle of incidence is. Turn the protractor right over there. Again, put it on the normal. And this time the 90 on the surface. And we're going to work our way across now, 10, 20, look at 0, 10, 20, 30, 40. I'm going to put a little tiny mark at 42. And you will put it at whatever your number was. Bella, what was your number? 38. That's fun. That's 2 on the other side of 40. You're not enjoying this? Okay. And now take your protractor away. And again, you can use the protractor as a straight edge. Again, from the point of incidence out to that point, draw your ray. And look at, I missed the spot. Terrible. Terrible. My picture does not reflect the law of reflection anymore because I made it 43 by the looks of it. That's okay, I'm going to lie. Angle, what do you think I'm going to put there? What do you think this ray is called? It's not the incident ray. It's the, outcident? Did you just say outsident? That is awesome. I have been teaching for almost 20 years, and no one has ever said outsident, Ray. But I like it. I like it. That is great. That is a great play on words. Nope, that's not correct, but I like it. The outsident ray. It's the, reflected ray. This is the reflected ray, also known as the outsident ray. Don't worry, on my video, Jake, I won't say who said that. Oops. I like outsident. Don't be embarrassed, it's awesome. So we're gonna call this angle R, a lowercase r. And I'm gonna put down 42 degrees. Why do I wanna write 44 every time? I have no idea. So underneath here, I'm gonna define angle R is the reflected ray, all right? And I'm now gonna write the law of reflection. Here it is, folks. Can you handle it? Everybody's excited? Angle I equals, what is it equal to? Angle R, dun dun dun, the law of reflection. All right, okay. So at this point, I'm gonna just stop this recording here for a moment because I'm gonna get you guys set up for doing the lab, all right? So I'm just gonna stop this here. It says that it's recording, I'll press stop here.